I will introduce our speakers as they come up. And the first speaker will be Professor Nithaya Chetty, with two affiliations at University of Pretoria, Physics Department, as well as Witwatersrand. And Professor Chetty will talk to us about just the title. Can you go?
That's quite fine. So I hope I'm audible. I know the time's very tight, so I'm going to be fairly quick. Just been given 20 minutes. So my name's Nithaya Chetty. The first name's a little difficult. So I'm currently the Dean of Science at Wits University. And I also hold an extraordinary professorship at my former institution, which is the University of Pretoria, which is where this work was done. So really, the focus here is on a relatively new bilayer material, which is called zeolite. A two-dimensional zeolite was synthesized for the first time less than a decade ago, and we're looking at some defect studies in this important material for technical applications. So my postdoc, Falana Andre Mbalaza, really did much of this work. She was sponsored by the Johnson Matthey company, and so I acknowledge a number of colleagues here who also participated in this project. And of course, thanks to the CHPC for making the computing facilities available for our work, but also big thanks to the CHPC for the support for the biennial school, the African School for Electronic Structure Methods and Applications that we've been running in various African countries over the course of the past 12 years now. The next school will take place in Kigali, Rwanda, middle of next year. That's based on quantum mechanical studies of material systems. So we began looking whilst I was at the University of Pretoria. I've just been Dean of Science now 3 years. 3 years yesterday, actually, kind of in but already very soon after the discovery, graphene was discovered in 2004. I began to work on graphene-related materials in 2008. So we got going fairly early on, and you know the incredible properties that graphene presents. It's a single atomic layer material, so it's truly two-dimensional. Synthesized for the first time in an incredibly crude and simple way. So one wonders why one was not able to do this already decades ago. But the real fascinating thing about graphene from an electronic structure point of view is that you have these linear bands that cross. It's a zero band gap material, and this gives rise to the effective mass of electrons at the top of the valence band having effective mass 0, which means that they can in principle reach ballistic speeds. The fact that it has a zero band gap is a problem. So a lot of the efforts over the past little more than a decade now has been to find ways in which you can open up a reasonable gap in graphene whilst maintaining the low effective mass. I would say that a lot of the defect studies have been based on that type of problem. So we've done some interesting work on graphene. This paper here continues to be cited quite extensively, more than 570 citations in a physical review thus far on mechanical properties of graphene and boronitrine. Basically, we defined a new property that's pertinent to two-dimensional materials. Essentially, it's nothing more than the two-dimensional equivalent of the bulk modulus. This laser point is a little not working perfectly. So pressure, of course, in three-dimensional sense is minus dE by dV. It has units of Pascal or energy per unit volume, force per unit area, that's pressure. But the two-dimensional equivalent of pressure is energy per unit area, which is force per unit length, has the same units as surface tension. So we went through looking at some of the original work by, sorry, I'm clicking this incorrectly, original work done by Birch and Monaghan going back to the 1930s and really derived the two-dimensional equivalent of the equations, defined a two-dimensional layer modulus, which is a material property. And for the first time, then do we have such a property that we ourselves invented and calculated for the first time, the layer modulus for graphene, which interestingly comes out to being the hardest from a two-dimensional sense. It mimics very much the three-dimensional equivalent of the bulk modulus. But once again, it's a totally new material property. The units, for instance, is very different. It's force per unit length. I'm not going to dwell on that for now. I really want to talk about a new two-dimensional material that has been discovered in 2014 by these folk. Annabelle is his first name, hard to say his last name, Boskobonic. Did his work in Germany, but I did meet with him at the Brookhaven National Lab some time ago when I was visiting. And I got to learn of this very interesting new two-dimensional material that they've synthesized. And I got to appreciate the importance of zeolites going back several hundred years, the three-dimensional equivalent. It's used a good deal in the petroleum industry as a catalyst. So I'll come to describing this a little bit more carefully, but basically it's a bilayer material. You can see there's two layers here of silicon and a layer above, in between and below of oxygen, and all of the bonds are completely saturated. It's basically silicon dioxide. And one looks at ways in which one can modify the catalytic properties of this material. So let's just dwell on the three-dimensional equivalent of this, which has been known, it turns out, since the 18th century. So zeolites have been used quite extensively. The basic building block is a silicon dioxide tetrahedron. And the tetrahedron, of course, can be oriented in various different ways, which results in a great many different structures, framework structures for these zeolite systems. But the interesting feature here are these pores. Can't quite see this laser point. Here you go. You have a microporous structure that becomes useful for the types of applications that zeolites have been used over a great many years now. Oh, I guess I've got a point there. That's probably it. So let's see if you can build up a secondary structure of these tetrahedra in various different ways, with the common oxygen atom basically connecting up the different tetrahedra, and it gives rise to some kind of local porous structure. And you put this all together, and it turns out you can build up quite a wide variety of different and fairly complex structures, but the common feature being silicon dioxide tetrahedra with fairly large pores. So these cavities then can be used for absorption of various different molecules, used for separation processes, molecular sieves, and those sorts of things. Clearly important processes for as we begin to explore more the aspects related to the green economy. So the essential chemistry for zeolites, three-dimensional and also two-dimensional, is that, well, firstly, the pristine system is not all that interesting. It's wide band gap material, as I've indicated, but traditionally it's silicon, it's aluminium doped silicon, and in so doing, then if you dope the silicon with an aluminium atom, the neighboring oxygen atom has a lone pair. So it's the reactivity. It has everything to do with this dangling bond state. And for instance, if hydrogen's attached to that oxygen, then the system behaves like a solid acid catalyst. Highly porous, so it can contain a variety of atoms from the point of view of storage, or just filtering as a filter, for example, in water purification systems. Large surface areas, I've already indicated the porous nature of the system. So that means that you have increased reactivity. Quite a wide variety of different applications, catalysts used in the petroleum industry. That catches one's attention very, very quickly these days, for nuclear waste reprocessing, gas separation, and so on. So as I indicated here, increasingly applications in the green economy, and chemists are very often asking the question, well, where are those cations located in such a system? So you dope, you have a dangling bond state, and where precisely are those cations that are associated with this system as a charge compensating element? So let's get to what we're interested in. I've got a point in this way. Your bilayer system, I'm going to have to go fairly quickly. Basically, I've already described it. From the side view, you have these 4-membered rings out of the plane, I guess, and then in the plane from the top view, you have the 6-member rings. So those then would be this kind of equivalent of these pores that you have in 3 dimensions. In 2 dimensions, just basically going to be a hollow type of site. All bonds are of course, fully saturated here. So you can look at the periodic table, and much of what's been done, much of what's been done is looking at hydrogen as, pardon me, looking at aluminium as the dopant, and hydrogen and first group 1 elements as the cations for charge compensation. But really now in our program, our project, we've begun to look at these systems more systematically. We've looked all the way down group 3 as possible dopants, and group 1 as possible charge compensators. So really, what we're having here is replacing your silicon atom with a group 3 element, and also then having a dangling bond state. This is not working perfectly well. My goodness. Here we go. Group 3. Aluminium traditionally being used, and we've in our work have looked at barium, gallium substituted silicon. We also then are looking at the nature of the chemistry at the dangling bond state, and really chemists are mostly asking the question, where's the cation located? And the various cations that we've considered beyond hydrogen are lithium. I've got a point in that direction. What is it? Hold it closer up. Yeah, closer up. Okay, got it. It's hydrogen, lithium, sodium, and potassium. And so we're principally looking at the chemistry of those elements. So we've used the quantum espresso codes in these schemes, a very standard type of choices for the different parameters, PAW potentials, exchange correlation potentials, included the van der Waals interactions, and interestingly, the bulk properties for the silicon dioxide bilayers zeolite came out to be very similar to that for the three-dimensional system. These parameters, 1.63 angstroms for the silicon oxygen bond length, very comparable to that for the 3-dimensional case. Also similarly for the silicon interlayer distance. So the band structure as well, giving you a wide band gap. Of course, in density functional theory, you're really usually going to have to be fairly careful about the exact value of the band gap, but this came out to being a wide band gap material consistent with a 3-dimensional system. So let's go on to doping these this bilayer system. We've looked at the dopants that I've already indicated, barium, aluminium, gallium substituted silicon. We've looked very carefully at the geometry. Turns out that the bond length for boron with silicon much shorter compared with aluminium silicon, shorter than gallium silicon, and that is understandable because barium, of course, is more electronegative than the rest of the elements. Interestingly, the formation energy for the barium substituted silicon came out to being exothermic, so it's fairly stable. For aluminium, which has historically been used in the 3-dimensional systems, was also exothermic, but for gallium, it is less stable, being endothermic. All of these defects, of course, are p-type defects. So really then, the question is, once you bring in the charge compensating atom, the question is where does it reside? Well, given the symmetry of the system, one could kind of surmise that the additional atom would very likely reside in a fairly highly symmetric environment. So we look specifically, we look specifically at the site above the hexagonal ring, the site above the oxygen that is bonded to the defect, and then we looked at the hollow site in the bilayer itself. And our conclusions then Well, we looked at this in a fair amount of detail. I'm not going to consider all of the different geometrical arrangements, but the conclusions were that in the fully relaxed geometry, the surface on top hexagonal site was marginally low in energy. Interestingly for us, all of these different high symmetric sites came out to be comparable in energy, but the hexagonal, the surface on top hexagonal site came out to being marginally lower, more stable. So really then we predict that each of these three sites would be very likely sites for additional cations to be located, the sorts of systems that you might want to consider in a water filtering process, for example. The electronic properties, of course, you would expect that these dangling bond sites would be saturated with the additional charge compensating defects. And what really happens is that these shallow defects remain within the gap, but this then can also be considered in a useful way as a means of engineering the band gap. So the additional considerations that we made, which begins to speak at ways in which this bilayer material can be used as a means for catalysis of various different forms. Interestingly, you could consider a situation where two next to neighboring silicon atoms are doped by say a group 3 element like aluminium, but any one of the other group 3 elements will do as well. And interestingly then, these two oxygen atoms both have a dangling bond state. This means then that you can have a situation where a alkali earth element, a group 2 element, could combine with both of those two oxygen atoms. So this just increases the possibilities of cations being absorbed and being available for various different chemical exchange processes, particularly in a catalytic reaction. So once again, we've considered the second column, beryllium, magnesium, calcium, Ba, barium, as the possible. I don't think we've done any calculations, barium as a possible +2 charge compensating states. But this also opens up the possibilities of such a system becoming useful for filtering of noble metals as well. We're currently looking at not just P-type dopants for the silicon dioxide system, but also N-type dopants. This increases and this has not been considered even in the three-dimensional case. I guess really what we're getting to is that the two-dimensional system is sufficiently ideal enough that enables one to do both from an experimental point of view, but also from a theoretical computational point of view, some fairly interesting ideal experiments. So in this instance, we're looking at replacing the silicon atom with an N-type defect like nitrogen, phosphorus, arsenic, and so on. And this opens up the possibilities of a whole range of other types of defects that could be attached to the system and become a means of filtering out such ions for a variety of different applications. So finally, then the silicon dioxide has given us the opportunity to think about a possible new phase for solid carbon dioxide. Of course, you know that carbon dioxide is in the gaseous form. To look at solid carbon dioxide, you would need to reduce the temperature, but that would still be a molecular system. If you want to look at a covalently bonded carbon dioxide system, would have to be under extremely under conditions of extreme high pressure. So silicon dioxide in this bilayer form provides the possibility of us to explore the question: can carbon dioxide exist in such a bilayer form under conditions of high temperature and pressure? Of course, it's easy from a computational point of view to compute the properties of carbon dioxide in the system. The real question is whether we can synthesize it or whether we can drive the system through a phase transition from one form of solid carbon dioxide, possibly in a molecular state, maybe unlikely, all the way through to this covalently bonded system. But this is what we're currently considering. Thank you, colleagues.
Thank you. Thank you very much, Professor Chetty. I think we have time for at least one question. Yes, oh,
Thank you very much. Very interesting talk. First, I have a comment. The Nosovelos and Gaim are in Manchester and not in Birmingham, as you wrote in this. I'm from Manchester, so just Northern England. Yeah. I just wonder. So you discussed about the surface tension at the beginning and your pioneering work on that. So for graphene, it's known that the surface tension of graphene is different than graphite. They can be considered like transparent in the sense that they support at the end determines the wettability of the graphene. Because this is a 2D material, will also need a support. Do you expect the surface tension to be different compared to the 3D version of zeolite?
Going to apply two-dimensional tensile force on two-dimensional zeolite, there will be a fair amount of bond stretching and so on. So we didn't really spend particular attention on this or use those methods for the two-dimensional system, but of course there would be considerable differences. The three-dimensional zeolite, structurally, they're just such a large variety. There are more than 300 different framework structures, so it does depend on which ones you're looking at. But two-dimensional, it's reasonably clean structure. We can indeed calculate the equivalent for the bulk modules for the system.
Thank you.
I'll chat later. I'm wondering with the zeolites, what are the advantages for shape selective catalysis from these kind of zeolites? Any more advantages? Shape selective catalysis.
So yes, the size of the pore. So I'm not an expert in catalysis. I've just approached this purely from a computational point of view. I guess theorists, especially physicists, like to see a nice ideal system. So that's the way in which we've considered. But I understand the size of the pores are very important. You want to look at, it's really in the end a physical thing. If you want to use the zeolites as a means of filtering out different types of atoms or different sizes of atoms, then it matters a great deal as to the size of the pores that you have, and of course the locations that these mostly cations for p-type dopants, mostly would be cations that you're interested in, that you can filter out, and then of course they become available for exchange processes in some kind of catalytic interaction.
Thank you. Later.
He will be available. It will be available during the lunch break as well. So I hope you can continue with your questions. And just from the CHPC, I think we would like to thank you for your contribution and participation. Thank you very much. Thank you.